All right, so we're going to go through a few examples of using distance and displacement, measuring them, calculating them, and different ways to report distance and displacement. So first things first, distance, remember, is just the total amount of the total length of a path traveled by some object. So for our first example, a dog runs 15 feet west and 25 feet east. That dog has traveled a distance of 40 meters, 40 feet. Right, that's pretty clear. So all we did was we added it up. Now note that there's no direction to the distance, right? It was just an overall amount of distance traveled by the dog. Now, as to the dog's displacement, there's a few ways to figure that out or to arrive at that. So first, let's look at a graphical method. So here's our starting point, and we're going to come up with a scale for our diagram here. Each box is going to represent 5 meters. So the dog first runs 15 feet west, which would correspond to 3 boxes to the left. Again, we're going to make the assumption that this direction on the page is north. All right. Now, the dog first runs 15 feet west, and then it's going to run 25 feet east. So that's going to be 5 boxes, and this is going to be the ending point. So you'll note that these lines really should be right on top of each other to show that the dog is actually running back and forth along a one-dimensional path. But I'm going to be drawing things slightly offset a little bit just to make it clear that there were 2 motions involved. So we can see graphically that the dog's final position is 10 feet to the right of where he started. So our final displacement, we could very easily just say 10 feet east. But we also have a tendency with one-dimensional motion to report things in terms of positive and negative. So there's sort of a general convention that we all agree on that says that things traveling to the east, we would say that that's positive motion. To the west, we would say that's negative motion. And correspondingly, if our one-dimensional system were aligned north-south, we'd say that north is positive and south is negative. If we had an up-down direction for our one-dimensional motion, we would usually call up the positive direction and down the negative direction. Now, again, these are just rules of thumb. This is all an arbitrary system. And you can change these things on the fly. You can decide for the sake of any one particular problem that you're going to call down the positive direction and up the negative direction. And there may be cases where that actually makes a lot of sense. So you're free to make these choices as you will. Just know that generally speaking, we usually call east, north, and up the positive directions, west, south, and down the negative directions. Also, to the right would be positive, and to the left would be negative. Common definitions. So here, as long as we all understood that that our system was aligned east-west and that east was positive and west is negative, we would be justified in saying that our final displacement is plus 10 feet. We can also set up a calculation to show this. So in general, the change in any quantity is equivalent to the final amount of that quantity minus the initial amount of that quantity. So here we could say that the final position or the final amount of something is equal to the initial amount of that thing or the initial position, and then added to any changes that occur as time goes on. So in this particular case, if we call our starting position the 0 position, our final position is the 0 position plus a contribution of negative 15 feet plus a contribution of positive 25 feet for a total final position of positive 10 feet. So you can see there are a number of ways to interpret this. The easiest way is often graphically, but once we get the hang of doing this just in terms of numbers, things get simpler. Okay, so next we have a boy walks 30 meters north, 50 meters south, and 80 meters north. So we have 3 motions going on there, 30, 50, and 80. Now, the distance traveled is simply the sum of all these motions, or 30 plus 50, 80 plus 80 is 160 meters. Okay. So we're going to call this our starting point, and we first go 30 meters north to point 2. Then we go 50 meters south, and here I'm calling each box 10 meters. So 5 boxes to point 3, and then we're going to go 8 boxes north to point 4. And see, this is a total of 160 meters that this person traveled. 30, 40, that's 80 meters, and then another 80 meters is 160 meters. Now, what's their final displacement? Well, once again, if we call the start the 0 position, right, we'll call start the 0 position, we can calculate this, where this person should be ending up. We would say that the final position should be equal to the initial position plus any changes in position that occur. So the final position is equal to 0. And then we have a contribution of plus 30 meters, because again, we're going to call north the positive direction. And then we go minus 50 meters and then plus 80 meters. Okay. So 30 minus 50 is negative 20, plus 80 is positive 60 meters. So our displacement is either 60 meters north of the start or positive 60 meters. Okay. And you'll notice that we can confirm this graphically. This is indeed 6 boxes away from the starting point, so 60 meters. All right, so a ball is dropped from a height of 5 feet above the ground, hits the ground, and bounces to a height of 3 feet. So our distance traveled is clearly 8 feet. We went down 5 feet and then back up 3 feet. Now, what's our displacement? All right, well, if we're calling the starting point 0, then our final displacement graphically we could see is 2 feet below the starting point. So let's say 2 feet below start, or we could say minus 2 feet, right? Both of these things would mean the same thing if this is our point of origin. Okay. Now, there is another way to look at this. What if we didn't want to call this the 0 point? What if we wanted to refer to the ground as if this were a position of 0? Well, now the starting point is not 0 anymore. The starting point would actually be a position of plus 5 feet. And if we do our calculation, the final position is equal to the initial position plus any changes. So our final position is equal to, now our initial position would be 5 feet, And then our first motion takes us down 5 feet. And then our last motion brings us up 3 feet for a final position of 3 feet, positive 3 feet. And this would be above the ground. Now notice that we're not saying that the ball actually stops at position 3. This just happens to be the motions that we're considering for the ball, right? The ball may do other stuff after it reaches position 3. It may start at 5 feet, bounce up, go to 3 feet, come back down, and keep bouncing or do other things or whatever. We're not concerned about that. We're only concerned about the motions that we've talked about, right? So from the start of when we were looking to the end of when we were looking, the displacement is either 2 feet below the start or 3 feet above the ground. And it depends. Like, we're perfectly justified in referencing it any way we want, as long as we weren't told a specific way that we were to reference it. All right, an object begins 30 meters west of a pole, moves 20 meters east, 60 meters west, and 75 meters east. So we have 3 motions. We're moving 20, then 60, then 75. 20 and 60 would be 80. 80 and 75 would be 155 total meters of travel. We need to draw a pole here. So just going to draw a pole here. Here's our pole. And here's the starting point, 30 meters west of the pole. So we're going to walk from there 20 meters east and then 60 meters west, 1, 2, 3, 4, 5, 6, and then 75 meters east, and that's going to be 6, 7, 75. So I'm going to place my little waypoints. So first we go from start to position 2, 20 meters to the east of start, and then 60 meters west of position 2, and then 75 meters east of position 4. And we can see that our final displacement, the point where we end up, is, well, where is it? Right, it's right here. So what is that point? Right, that's the question. So there's a couple of ways we can say this. We could either say we're plus 5 meters from the pole, or you could say 5 meters east of the pole. We could also say we are plus 35 meters from start, or we could say 35 meters east of start. And all 4 of those things would be equivalent, right? Our displacement or change in position is allowing us to figure out what the final position is, right? So our final position is our initial position plus any changes. Well, what's our initial position? Are we calling the start 0, or are we calling the pole 0? Right? If we're calling start 0, then our initial position is 0, and this calculation is going to give us a final answer of plus 35. If we call the pole 0, then that makes our initial position not 0, but minus 30 meters. And this calculation is going to give us a final answer of plus 5. Right, so again, we just have to be clear where we're referencing from, and these things are relatively arbitrary, right? We can call the point of origin anything we want, and this would all make sense. And our final answer would be referenced from some specific point of origin that we choose in the problem. Okay, so things get a little more interesting when we start doing things in 2 dimensions. So now we have a man walks 30 meters north and then 30 meters west. So the distance traveled is, again, just the sum of those 2 things, or 60 meters. Okay, now, if the person starts here and walks 30 meters north to position 2, and then 30 meters west to position 3, they do this. The displacement is definitely not 60 meters. They're definitely less than 60 meters from where they started. In fact, to determine the displacement, I would draw this line. This is the displacement. And if I wanted to calculate that displacement, I could quite easily. That would be, I would use the Pythagorean theorem to do it, and it would be the square root of 1,800 meters. This would be the most accurate way to write it. I could also take the square root of 1,800 and say that it is about 42 meters. It's less accurate, but we do need to do this in physics class. So the displacement, or the magnitude of the displacement, is 42 meters. So the person is 42 meters from where they started. But this is a displacement, so it must include direction. So now how are we going to specify direction? Well, this is, if we make this north, and this is east over here, and that makes this west, since there's an equivalent amount north and an equivalent amount west, we could just say 42 meters northwest. Right? It would not make sense to call this positive and this negative, right? Because you can't actually add and subtract these things. It's not one-dimensional motion. However, if you watch the lesson on unit vector notation, or you know something about unit vector notation, you know that the easier way to write down this displacement is actually to say minus 30 meters I hat plus 30 meters j hat, because 30 meters I hat plus negative 30 meters I hat plus 30 meters j hat. We all know what that means. That means if you want to represent the path traveled by this person, start here, go 30 meters in the negative x direction and 30 meters in the positive y direction. And that's where you ended up. And you could calculate what the how far that person is from where they started. You just use the Pythagorean theorem. And you could determine what the angle of travel is. You can determine the direction in which that person is from the sides of the triangle. Okay. So let's do one more example. So an object travels 200 meters east and 900 meters south, 700 meters south. So that's a total distance of 900 meters. So let's move these things around. So we're going to start here. We'll go 200 meters east and then 700 meters south. 1, 2, 3, 4, 5, 6, 7. So 200 meters east, followed by 700 meters south. And to write the displacement, the easy way would just be to say, well, we have a displacement of plus 200, oh, sorry about that. So we would say 200 meters I hat minus 700 meters j hat. Now that's exactly what this means, right? This is the easiest way to write the displacement. There are other ways to do it. So we could, let's say we were asked, how far is the object from where it started? Well, now this answer is not good enough anymore. You can't say this when you want to answer the question, how far is it from where it started, right? This is a displacement. This is not a distance, and how far it is from where it started is a distance. So we would actually have to use the Pythagorean theorem to calculate this. And what you'll find is that the Pythagorean theorem in this case gives us an answer of about 728 meters. So the distance from start to where this thing ends is, in a straight line, is 720 meters. So the magnitude of the displacement is 728. Now, if we wanted to give the displacement using cardinal directions like north, south, east, and west, what we could not say is 728 meters southeast. This is not right. Okay, why is that not right? Because when you look at a compass rose, southeast has a very specific definition. That means a line exactly between south and east. So 45 degrees south of east or 45 degrees east of south. So this does not fit that definition. So if you wanted to know how to specify this using an angle, what we have to say, what we have to do is determine what this angle is. Okay. Now, in order to do that, you have to know some trigonometry. So you could use sine, cosine, or tangent if you know all three sides of the triangle. I tend to like to use tangent. So the arctan, or inverse tan, of the opposite over the adjacent, 700 over 200, or even just 7 over 2, is about 74 degrees. So your final answer to this could be 728 meters at 74 degrees south of east. And there you go. A little bit about distances and displacements, how to calculate them in 1 dimension and 2 dimensions. You should get plenty of practice with this in class and during regular lessons. But in case you need more,